All right, my friends, welcome back. I just realized today is the 30th time we have met together, which means we only have like 10 more after today before the end of the semester. But don't worry, because if you're taking 352, you still got another 41 lectures coming your way in the next semester. All right, well, today we are moving on to chapter 11, where we will talk about oxidation and reduction. We'll spend most of our time on reduction today. We'll do oxidation on Wednesday. If you remember from general chemistry, what was your definition of oxidation in general chemistry? Loss of electrons. Now, it turns out that that definition is still true in organic chemistry, but we often don't think about it necessarily that way. We look for other telltale signs of oxidation in organic molecules. So the first is a decrease in the number of carbon-hydrogen bonds. Why does that count as oxidation? Because we're going to, from the oxidation reduction perspective, we're going to consider as though carbon owns both of the electrons in the CH bond. Now, I know already some of you are like, hey, wait a minute, formal charge, an atom owns half of the electrons in its bond. And you're right. We have a different way of counting electrons for oxidation state. We're not going to learn it for carbon, but we are going to pay attention to the loss of CH bonds as a sign of oxidation. Another sign of oxidation, which can occur either together with or independently of loss of CH bonds, is an increase in the number of bonds between carbon and a heteroatom, where we're talking about particularly electronegative heteroatoms, that is, things that are more electronegative than carbon. We're talking oxygen, nitrogen, halides, and so on. So that's how we're going to detect oxidation. And then reduction, of course, is just going to be the opposite of that. You will see that in organic chemistry, reduction means an increase in the number of carbon-hydrogen bonds and, or at the same time, a decrease in the number of carbon heteroatom bonds. So let's talk about how this might manifest itself for simple organic molecules. The most reduced form of an organic molecule that you're going to encounter is, of course, this alkane, which has a formula C4H10. If we remove 2 hydrogen atoms, that's going to count as oxidation. And by hydrogen atom, I mean removing a proton and an electron. If we remove 2 of them, we can oxidize the alkane to an alkene. Now, we're not going to learn how to do that oxidation reaction yet. We'll learn a series of reactions in our last chapter this semester that will enable you to take an alkane and convert it to an alkene. But today we will learn a reaction, the reduction reaction, where you can convert an alkane into, you can convert an alkene into an alkane by adding hydrogen, and we'll call that a reduction reaction. So alkenes or olefins are oxidized relative to alkanes. Similarly, if you take the alkene and you the carbon molecule with the carbon-carbon double bond, and you remove two other hydrogens from it, you can get the alkyne, which has a formula C4H6. And you can see both times we're losing two hydrogens, okay? It turns out you already know a series of reactions that allows you to oxidize an alkene to an alkane. You just didn't appreciate it as an oxidation reaction yet. So if you remember, you can first brominate the alkene to get the vicinal dihalide, and then you can use two equivalents of a strong base to do the two E2 reactions that give you the two pi bonds of the alkyne. So now you know that that reaction series, in particular the bromination reaction, was an oxidation reaction because it led to a decrease in the number of CH bonds and C heteroatom bonds in the molecule, or an decrease in CH bonds, increase in carbon heteroatom bonds. All right, questions about that? Yes?
So doing that get us from an alkane to an alkyne, or
So doing this gets us from an alkene to an alkyne. We have not yet learned how to take the fully saturated alkane and turn it to the alkyne.
by replacing both those bromines, well, with like two elimination reactions, would it give us two extra bonds?
So let me draw the intermediate. Is this. And then in the second step, you add NaNH2 and you do the two elimination reactions. So I'm not seeing where the alkane is coming from, sorry.
Okay. I think I see what
Yeah, so in this step, we increase the number of carbon heteroatom bonds, so that's a reduction. I guess, oh my gosh, I'm going to get that wrong so many times. We increase the number of carbon bromine bonds, so that's an oxidation. The second step is two elimination reactions. And when you lose a hydrogen and an adjacent leaving group, that's not a reduction or an oxidation reaction. Yeah. Okay, yes?
You have to have a sum total difference. So if you lose a CH and you lose a CBr, it's just what it is. It's not going to be either one.
Right. In an elimination reaction, that's neither oxidation or reduction, because though you're losing, it's neutral because you're losing a CH bond and you're losing a CBr bond. Neither oxidation or reduction. And that one's difficult to see. And I'm not going to actually show you a vicinal dihalide and an alkyne and saying, is this an oxidation reduction reaction? But I could show you an alkene and an alkyne and say which one is more oxidized. Yeah?
So you're basically just looking at the reactants and products and seeing the CH or C bonds to understand.
Yep, you're looking at the reactants and products, CH bonds and CZ bonds to see whether it's oxidized or reduced. Yep. Okay, and we'll see today a reaction that can actually add two hydrogens to an alkyne to do the reduction of an alkyne to an alkene. Okay? Let's look at another way that oxidation reduction manifests itself in organic molecules. We won't learn how to do this yet, though we will learn something about a related reaction towards the end of the semester. But we can actually oxidize the alkane to an alcohol. And if you look at the formula for an alcohol, it's C4H10O. We actually haven't lost, well, if you pay attention, we've lost one CH bond, and we replace it with one CO bond and one OH bond. So that's oxidation in two ways, because we've lost the CH bond and we've replaced it with the CO bond. So an alcohol is oxidized relative to an alkane. You'll see that if we remove two hydrogen atoms, that's oxidation of the alcohol to an aldehyde. The aldehyde's formula is C4H8O, so you can see the loss of the two hydrogen atoms. Of course, if we add two hydrogen atoms to the aldehyde, we can reduce the aldehyde to the alcohol. We will learn how to do oxidation of alcohols to aldehydes in chapter 11, but we will not learn how to reduce aldehydes to alcohols until 352. And then if we take the aldehyde and we add an oxygen atom to it, we can convert the aldehyde to the carboxylic acid, where again we have lost one CH bond and we've gained one CO bond. We also have gained OH bond, but these are the two that allow us to tell that it's been an oxidation reaction. We will again learn in 352 how to reduce a carboxylic acid to an aldehyde, but we won't learn that in chapter 11. Okay, so you need to get used to looking at molecules, comparing them, and seeing the change in oxidation state. That is alkane oxidized to alkene, which can be oxidized to alkyne, or alcohol, which can be oxidized to aldehyde, which can be oxidized to carboxylic acid. Okay. Questions? All right. Let's talk about, today we're going to focus on the reduction reactions. So we're going to start with reduction reactions of alkenes to alkanes, and then we'll also do reduction reactions of alkynes. You'll see that we'll have multiple methods for reducing alkynes. One that gives us the alkane, we do 2 rounds of reduction, and then 2 methods that take the alkyne and convert it into the alkene. Just as a word of warning, today in reduction reactions, we're not actually going to learn a lot of mechanisms. The mechanisms are sometimes complicated or aren't really necessary and aren't really worth the time that we spend. So I'll give you some clues about how the reactions happen or what the key features are, but you may need to memorize some of these details, and if that's true, you should just do whatever works for you for memorization. If flashcards are helpful, that can be a useful strategy. So, reaction number 1 is hydrogenation. And we'll start by saying hydrogenation of alkenes. Pay attention to the names of these reactions. They will often tell you what the reaction does. Hydrogenation of alkenes is going to be adding hydrogen to a carbon-carbon pi bond. And it's going to be a syn addition. So you learned on exam 2 that it is thermodynamically favorable to take hydrogen and add it, I'll just write H2, add it across a double bond to convert an alkene into an alkane. And you learned that because the two carbon-hydrogen sigma bonds that you form are more stable than the carbon-carbon pi bond that you break, and the hydrogen-hydrogen sigma bond that you break. But this reaction, but if you put hydrogen in with an alkene, they'll sort of sit there and stare at you indefinitely because though the reaction is thermodynamically favorable, it's pretty slow. And so we need a catalyst to accelerate the reaction. So the catalyst here is the transition metal palladium, which has the symbol PD. And this is palladium in its zero oxidation state. That means it's palladium metal. Sometimes people will represent it with a superscripted 0 to indicate that it's at the zero oxidation state. It's palladium metal. But sometimes people will just write PD, and that's fine too. The reaction is what I'm going to call heterogeneous, meaning that the palladium metal doesn't dissolve in the solvent that you're using. And as the reaction needs to allow the palladium metal to find hydrogen, and then the hydrogen reacts with the palladium surface, and you have two different palladium hydrogen bonds on the surface of the metal. And then the alkene has to find the surface of the metal, sit down on the surface of the metal, and then the metal delivers the two hydrogen atoms to the same face of the alkene. That mechanism that I've just described in words, you don't necessarily need to have an idea of, other than that it's a syn addition. Yes?
Is there supposed to be a second H on that bottom one?
Yeah, I missed one of them. Supposed to be a methyl group, sorry.
Okay, sorry.
Yep. My bad, thanks. Okay. So anytime you need molecules to react at a surface area is a big deal. So you don't just throw a chunk of palladium metal into the reaction. It's actually more efficient to have that palladium metal be finely divided as a powder. And in practice, what people do to stabilize the metal and to make it easier to work with is they'll grind up palladium metal with charcoal. You get palladium immobilized in carbon. And so that's going to be written as, or palladium adsorbed onto carbon. And that's going to be abbreviated as PD/C, palladium on carbon. And you can buy this in a bottle from a chemical supplier company. You can weigh it out. It's a convenient way to deal with palladium. All right, so that does syn addition of hydrogen across the pi bond. Just to give you a little practical view of how this reaction gets set up, you have a round bottom flask. And at the bottom of that flask, you have your palladium metal and carbon, charcoal. It's black, finely divided black dust. Then you have your solvent, whatever it is. You have your alkene. But as you know, hydrogen is a gas. And so how do you deal with that? There's multiple ways to deal with it, but the most common is to put a stopper in the top of your flask. And then you take a syringe with a needle on it, and the needle punctures the rubber stopper. And then attached to the syringe, and you kind of have to use a lot of tape for this, you put a balloon that is filled with hydrogen. And some labs have hydrogen gas tanks. You literally fill up the balloon like you would a helium balloon, only it's hydrogen. You tape that to the end of the syringe and you stick the syringe in the reaction vessel. That provides 1 atmosphere of air pressure, of 1 atmosphere of pressure that pushes the hydrogen into the round bottom flask and allows it to react. For some reactions, you need higher pressures of hydrogen, and you can use special reaction vessels that can be pressurized. One of the practical problems of this reaction, this hydrogenation reaction, is that it's difficult to weigh a gas, right? In fact, hydrogen's lighter than air, so you can't weigh it out. So how do you supply exactly the right amount of hydrogen? And the answer is you don't. You just use an excess. So it's assumed when you show hydrogen and palladium on carbon, it is assumed that you mean that you're using an excess of hydrogen. Some of you, as I introduce another reaction, are going to say, couldn't I just use one equivalent of hydrogen to get what I want? And I'd be like, sure, if you know how to weigh out 1 mole of hydrogen for every mole of starting material, which you don't. We were talking at the 8 a.m. class. Anybody remember how much volume one mole of hydrogen takes up? Something like 22 liters or something like that. How do you fill up a balloon with just 22 liters? Like, I don't know, it looks more like 21 to me. Like, it's kind of hard to do. So in practice, we just use an excess. Okay, so this reaction reduces alkenes to alkanes and if you make a stereocenter, you need to show the result of syn addition. Of course, if they're not stereocenters, you won't be able to tell. So this reaction is used a lot in the food industry, and we talked about this before. So in our chapter on non-covalent interactions, you recall that, I need to erase some stuff. You weren't looking anyway, so there we go. Da-da-da. Right, this is a slide from a previous chapter on non-covalent interactions and functional groups. We talked about how saturated fats are solids because their flexible nonpolar tails can more readily get close to each other and engage in stronger van der Waals interactions, whereas unsaturated fats and oils with the pi bonds in the nonpolar sort of tails, those pi bonds decrease the flexibility of the nonpolar tails. They make it harder for the nonpolar tails to approach each other. They weaken the van der Waals or dispersion interactions, and therefore unsaturated fats and oils tend to be liquids at temperatures where saturated fats and oils are solids. You guys remember that? Sort of good there. Okay, so behold, peanut butter. We have a jar of Skippy and a jar of Adams 100% natural peanut butter with 8 grams of protein per serving and non-GMO or something. So the difference between Skippy and Adams, you can see, is that Adams has a layer of oil at the top of it. Skippy does not. Okay, so the reason for this is, you will see if you look at the label for Skippy, I needed to bring my readers. This happened to you, don't laugh, because as soon as you turn 45, you can't read things up close anymore. Roasted peanuts, sugar, hydrogenated vegetable oil, including cottonseed, soybean, and rapeseed oil to prevent separation. So what they're doing here is they're doing the hydrogenation reaction with hydrogen and some catalyst. Not sure what the catalyst in the food industry is, but you could use palladium on carbon. They'd have to be careful because they don't want you to eat palladium afterwards. But if you do this reaction, you turn the vegetable oil from being unsaturated, liquid, to saturated, solid, then you can stir it up with the peanut solids and it doesn't separate out. Okay? So if you read hydrogenated vegetable oil on your food products, that just means they've done this hydrogenation reaction and that makes the oil more of a solid, which can be convenient because Skippy, when you're really tired and lazy in the morning and all you want to do is spoon feed yourself peanut butter, you don't have to stir it up. By the way, spoon feeding yourself peanut butter is not a sign of depression or sadness or it actually can help. So this summer, my son and I were hiking the Teton Crest Trail, and we'd never done it before. I hadn't really trained to be a backpacker. Our packs were too heavy because I had to also pack with myself my sleep apnea device. If you want to know whether I'm a nerd, yes, I am. At night, I sleep with this. But it's awesome because I sound like Darth Vader, so I'm happy. But anyway, so I'm packing all of this. On our second day, we were like 3 miles from our campsite, and I was so tired. We were in this South Cascade Canyon, and it's so beautiful, but my son says I was crashing out, which I know that's what it is. And we finally got to what I now call Existential Crisis Falls, and I had to just sit down, and then we got into our bear canisters and started spoon feeding ourselves peanut butter and honey, and all of a sudden life was better. So it is said that if you hate everyone and everything, you need to eat. And if you think everyone hates you, you need to go to sleep. And that will solve most of your problems. So that's my advice to you. But when you're at Existential Crisis Falls, you don't want to have to be stirring your peanut butter. Ain't nobody got time for that. So Skippy, right? Now, the second reason the food industry wants to hydrogenate oils is because of shelf stability. If you look, I bought these pre-pandemic. I'm not exactly sure when, but Skippy, the jar says best if used by May of 25. And this has never been opened, so chances are if we open it now and take a big spoonful, it's probably okay. Food labels are mostly pirate code guidelines anyway, right? It's got to pass the smell test, but if it does, you're probably okay. In contrast, the expiration date on Adams is November 11th, 2021. So that's 4 years out of date. Why is the expiration date so different? And the answer lies in the presence of those double bonds. So double bonds are reactive. You haven't learned this chemistry yet, but in particular, the allylic carbons adjacent to the pi bond are especially reactive. Molecular oxygen, which basically reacts as though it were a diradical, is able to remove a CH bond, oxidize the oil, and ultimately you convert that into this allylic peroxide, which is associated with being rancid, which is the gross taste of oil that's too old and's been oxidized. So to provide increased shelf stability, the food industry will often hydrogenate oils. No double bond, no allylic oxidation, no rancidity. The drawback is that saturated fats are not as healthy for you as unsaturated fats are, and another drawback is if they don't do the hydrogenation process completely, some of the double bonds actually isomerize from cis to trans, and that's where you get trans fats from, and they're associated with negative cardiovascular outcomes too. So if you want to avoid all of that, you got to be stirring your peanut butter. But if you don't care, then go for Skippy. And there are some peanut butters now where they've added a different kind of emulsifier. So they say, hey, this has all natural peanut oil, but you still don't need to stir it. I don't know what the emulsifier that they've added to. It's probably something. Could be soap. Yeah, probably they use soap. Probably not soap. It may be some kind of lecithin or egg or something. Okay, so in a previous year, I was like, anybody want to come take a swig of this delicious yellow peanut oil at the top of Adams? And immediately someone was like, extra credit? And I'm like, okay, on second thought, no. So There they are. I want to still have these peanut butter. I want to still have these jars of peanut butter 20 years from now when I'm teaching your children organic chemistry. And expiration date 2021. All right. So let's talk about alkyne hydrogenation. There are basically three methods for alkyne hydrogenation or alkyne reduction. The first is alkyne hydrogenation using palladium on carbon. This will take the alkyne all the way. First, it will reduce the alkyne to the alkene, but because the catalyst is so reactive, you can't stop at the alkene, but you instead go on to the alkane. So, palladium catalyzed hydrogenation of alkynes adds 2 equivalents of hydrogen to the alkyne. So that's what happens if you use palladium on carbon and hydrogen. You first add 1 molecule of hydrogen to reduce the alkyne to the alkene, and then you add a second equivalent because you already know alkenes react. The alkene will react again with a second equivalent of hydrogen to give you the alkane. Now, a question that people want to ask is, could I just add 1 equivalent of hydrogen? And the answer is sure, if you could measure it out, but that's often impractical. And then you also worry about getting a mixture of products, because as soon as you form some alkene, the alkene you form is going to go on and react with the remaining hydrogen, and so you'd likely get a mixture of products. Yes?
If you're using palladium, will the reduction always go to an alkane?
If you're using hydrogen with palladium on carbon, yes, the reduction will always go to an alkane. Now, the question is, what if you wanted to stop at the alkene for whatever reason? And we have a couple of conditions for that. So, to stop at the alkene oxidation state, the first method is also a catalytic hydrogenation, but you use what's called a poisoned catalyst. And this represents a strategy chemists sometimes use where you're like, okay, the catalyst doesn't quite do what I want, so what if I add some things to it? What if I add some things that should slow down the reactivity of the catalyst? So there's a catalyst whose structure is not really important for us. It's palladium metal with some additives that slow down the reaction. It is called Lindlar's catalyst. Your text will actually say what some of the catalyst poisoners are, and we don't care. We'll just remember Lindlar's catalyst. It will take the alkyne and it will add only 1 equivalent of H2, and it's a syn addition because, again, it happens at a metal surface, but this allows you to stop at the cis alkene, always. So if you wanted to reduce an alkyne, if you wanted to reduce an alkyne to an alkene, you can use the Lindlar catalyst with hydrogen, and that will give you the cis alkene. That's a reaction with a stereochemical outcome. And I will ask you questions that will require you to have mastered that stereochemical outcome. So if you memorize that hydrogen and Lindlar's catalyst gives you the alkene, that's insufficient. You need to know that it always gives you the cis alkene. And I'll show you how we're going to test that. Yeah,
Is that just because it's sin addition?
exactly. Yeah, it's just a syn addition. Yep. So the hydrogens have to end up on the same side of the original double bond. Yes?
Is that specific to Lindlar's catalyst or all poison catalysts?
That's, okay, that's an interesting question. Is that specific to Lindlar's catalyst or all poisons catalyst? Lindlar's catalyst will be the only poison catalyst we use in this chapter, so the answer is yes and no, it doesn't matter. Okay. Others? All right, what if you wanted to get the trans alkene? So this one is weird, but the product is the trans alkene. So I'll show you this product, and we will not be responsible for the mechanism here. It is known, and it's in your text, but I decided that it wasn't worth the time we would have to spend to talk through it. So this reaction involves sodium metal, which people will just write as Na, or if they're really trying to help you out, they will write Na with a superscripted 0. But your text will not usually use that superscripted 0. That indicates that the sodium is not sodium plus, it's neutral sodium in its metal oxidation state. The other component of this reaction mixture is liquid ammonia. So that ought to be, both of those things ought to sound a little bit scary. Ammonia is a gas. When you go buy ammonia from the store, what you're buying is ammonia gas dissolved in water. It becomes ammonium hydroxide. But it has this sort of characteristic acrid smell, and that's some of the ammonia coming off the solution as a gas. If you want to have liquid ammonia, you have to cool down the temperature really low. And so you need a flask that's like in a ice bath with dry ice or something like that, a dry ice bath, or something super refrigerated so that the ammonia gas can condense on the inside of your flask. Then sodium metal, as you know, is not a friendly reagent either. You've probably, if you've ever watched YouTube as a teenager, you probably looked up what happens when I throw a chunk of sodium metal in the lake. And you see some dude does it, and then it shoots out of the lake and continues to shoot out of the lake because sodium reacts with water and oxygen in a very vigorous and exothermic reaction. So this is difficult to do. But when you do, when you dissolve the sodium in liquid ammonia, it doesn't go on fire, interestingly enough, at least at really low temperature. Instead, what happens is the sodium metal loses an electron, ejects an electron. Where does that electron go? It turns out that the electron is shared by a cluster of ammonia molecules. You didn't know this could happen, and neither did I before I learned about this reaction. Basically, a cluster of like 8 to 10 ammonia molecules hydrogen bond with and share the electron. That arrangement of atoms has a characteristic deep blue color. And you can go Google it on YouTube. The reaction is called basically the dissolving metal reduction of an alkyne. And it always gives you the trans alkene. We're not going to talk about, I'm not going to hold you responsible for what happens to the sodium metal or the idea that there's an electron flowing around in solution. I'm also not going to hold you responsible for the mechanism. The reason you get the transalkene is because this reduction happens in steps. You first add an electron from solution directly to the alkyne. It hops into one of the antibonding orbitals of the alkyne. Then the alkyne's negatively charged. So it picks up a proton. It steals a proton from probably the liquid ammonia. And then now it's neutral. Then a second electron hops into a partially filled orbital. It becomes negatively charged again. You have an intermediate that can be protonated either from one face or the other, and it's selectively protonated from the face that gives you the more stable transalkene. You don't need to know that mechanism, but the fact that it's stepwise allows you to get the more stable transalkene product. Okay? One word of warning about this reaction. If I were to just write it like I would in a practice problem, I would just write sodium, comma, NH3. Students typically confuse that with another reagent we have seen recently, which is NaNH2, no comma. NaNH2, no comma means sodium and the conjugate base of ammonia, which we're using as a strong base. We have used that before in a reaction where we took a vicinal dihalide and made an alkyne. I don't know if you remember that, but I'll just write it here just for your reference. We used 2 equivalents of this strong base to do the 2 tandem elimination reactions that give us an alkyne. So sometimes, because NaNH2 already has a connection in your mind with alkynes, students sometimes get confused about this set of reagents, which look similar and also have something to do with alkynes. So you're gonna have to do whatever it takes to keep those straight. I'm just warning you of a potential source of confusion. Okay. I want to show you how I can use these 2 different reactions with 2 different stereochemical outcomes to test your understanding of reactivity and stereochemistry. So, using alkyne reduction correctly in synthesis. We're going to do this in the forward direction. And it will seem totally obvious to you, and then we'll try it in the reverse direction, and you'll probably see how it's not so totally obvious to you. So if you take this alkyne starting material, and if we use the Lindlar catalyst, that takes us from the alkyne to the cis alkene. If we then use that to do a halogenation reaction with Br2, that's a chapter 10 reaction, that's going to do anti-addition of Br2 across the pi bond. And if you draw the molecule in exactly the same shape as the original alkene was, then you show the anti-addition product simply by having the BRs be on opposite sides. This product is chiral, and there is its enantiomer. Okay? Now, let me demonstrate how I could deceive you, because I'm evil, but since you got me monologuing, I'm going to disclose all my evil secrets before you. What if I draw this same product in the following way? And what if I don't show you what the reagents are? That is dastardly. It is the same, if you can see it, but here's the thing that will happen to you if you are going too fast. You are going to see this. Your brain will say, I know, transalkene. And you're going to propose the wrong reaction. What would happen if I did first sodium metal, the dissolving metal reduction, sodium metal and ammonia to get the trans alkene? And then what would happen if I did bromination? I would continue to draw the molecule in the same shape that it was when it was an alkene, and then I would need to show the BRs being on opposite sides. Oh, freak is right. Do you see the two things you had to get right? You had to get right alkene stereochemistry and also anti-addition of Br2. If you're in too much of a hurry, you will miss the fact that these two were not on opposite sides. So to think back correctly, you would need to redraw the molecule such that the BRs were on opposite sides, and then you could think backwards to the correct alkene stereochemistry. Does that make sense? Yes?
So to double check our work to make sure we're not getting tricked, is it helpful to go through like the mechanisms and the intermediates?
So one of the question is to double check your work. Is it helpful to go through the mechanisms or draw the intermediates? You won't know the mechanism of the hydrogenation step. You do know the mechanism of the bromination step. So sure, if you can do that mechanism where you show the bromonium ion intermediate and you show that being opened up from the back side, that can be tremendously helpful. I'll just encourage you to check your work. If you think backwards and propose a synthesis, at least check your work and do it in the forward direction so you make sure you get the stereochemistry right. Other questions about that? I mean, I really encourage you to practice that because you're all sitting out there nodding your heads. But I guarantee that when you're alone in the fog of war, it will seem a lot less clear to you. So, yes? So, what I drew on the bottom just shows you that this approach doesn't give this product. However, if I wanted that product, that reaction is totally fine. In other words, if I desired to get this particular dibromide with the stereochemistry as shown, then yes, the dissolving metal reduction followed by halogenation is the correct way. By the way, remember that I could also draw this in the dastardly conformation that conceals the true identity of the stereochemistry you need to use. Practice this, because guess what? Next time we're going to learn a few other reactions we can do with alkenes, and they also have stereochemical consequences, so there'll be more ways we can mix this up. All right, have a good Monday. I will see you Wednesday.